Hello everyone, welcome to my YouTube channel. I love engineering. This YouTube channel is all about microwave engineering. In this video, I'm going to explain some of the basic concepts of the microwave engineering. Here, on the slide 1, equivalent circuit model of linear time invariant two-port network is presented. If you observe this equivalent circuit model, it is a linear time invariant system. Actually, in general, to analyze any kind of two-port network in microwave engineering, we consider equivalent circuit model of that network. It may be any network like power amplifier, oscillator, filter, anything. So, if we consider any kind of two-port network, this is the equivalent circuit model. Here, Vs, VL are the load and source voltages. Zs, Zl are the source and load impedances. V1 and V2 are the voltages that caused due to the excitation of source and load voltages. I1, I2 are the currents that traveling towards the circuit. The first equation in this slide is matrix M multiplied with matrix V plus matrix N multiplied with matrix I. If you sum it up, then it is equal to 0. Here, matrix M and N are independent of source and load impedances, Zs and Za, and voltages VL and VL respectively. Matrix M is non-singular matrix, so mod M is not equal to 0. Then this matrix equation can be rewritten in terms of current. If you rearrange the equation above, we can get voltage matrix is equal to negative inverse of matrix M multiplied with matrix N multiplied with current matrix gives us the impedance matrix multiplied with current matrix. If you consider the scalar form of these equations, we can get V1 is equal to Z11 I1 plus Z12 I2. V2 is equal to Z21 I1 plus Z22 I2. Here Z11 and Z22 are open circuit driving point impedances, and Z12 and Z21 are the open circuit transfer impedances of two-port network. What is the main difference between driving point impedances and transfer impedances? Let us consider first about transfer impedances. Here Z12 and Z21 are the transfer impedances. What is the notation Z12 exactly mean? Z12, here 2 means port 2, 1 means port 1. So Z12 means it is an impedance that is influenced by the port 2 on port 1. Similarly, Z21. And if you remember the circuit, which I have shown in the slide 1, V1 and V2 are the voltages that caused due to the excitation of V source voltage and load voltages. In other ways, in other words, we can also say that it is a cause of due to the input current I1 and I2. The open circuit driving point impedance are determined by setting I1 equal to 0. Similarly, the transfer impedances are determined by setting I2 equal to 0. By substituting I1 equal to 0 and I2 equal to 0 in the above equation, we can get the result Z11 equal to V1 divided by I1 where I2 equal to 0. Z22 equal to V2 divided by I2 where I1 equal to 0. Z21 is equal to V2 by I1 where I2 equal to 0. Z12 equal to V1 divided by I2 where I1 equal to 0. Admittance matrix. What is admittance? It is just the inverse of impedance. To derive the short circuit admittance matrix, when the circuit in the circuit current components I1 and I2 are considered as outputs caused by V1 and V2. Here I1 and I2 are the currents, V1 and V2 are the voltages. Matrix N is also non-singular matrix. So mod N is not equal to 0. So current matrix equal to negative inverse of N matrix multiplied with M matrix and with voltage matrix. To sum it up, it's just the inverse of admittance matrix. That equal to multiplication of Y matrix multiplied with V matrix. Y matrix is the short circuit admittance two-port network matrix. The scalar form equations are given below. I1 equal to Y11 V1 plus y1 to v2, I2 equal to y21 v1 plus y22 v2. The open circuit driving point admittance are determined by setting v1 equal to 0. Similarly, the open circuit transfer admittance are determined by setting v2 equal to 0. If we substitute these two voltages in the above equations, we can achieve these results. Y11 equal to I1 divided by V1, where V2 equal to 0. Y22 equal to I2 divided by V2, where V1 equal to 0. Y21 equal to I2 divided by V1, where V2 equal to 0. Y12 equal to I1 divided by V2, where V1 equal to 0. Scattering matrix. Analyzing the scattering matrix is very important to understand any kind of circuit with in microwave engineering. Scattering matrix makes us to understand very important concepts like gain, return losses, etc. Insulation, insulation, like many things. If you consider the equivalent circuit of single port network, uh, there is an equivalent circuit of single port network in the slide. Here, Vs is the source voltage, Zs is the source impedance. When you apply a voltage source across the load, which has impedance Z according to the figure in the slide. So when you apply the voltage across the Z, then current I flows in the circuit. Generally, if you consider scattering matrix, it gives lot of information about the incident waves and reflected waves. We consider current and voltage as a incident waves and reflecting waves as a traveling waves in the circuit. So, if you apply voltage Vs across the load Zs, which Z is the impedance, then the voltage wave travels towards the load, and some of the voltage wave that travels towards the low is reflected back. So here Vi is the incident voltage wave, Vr is the reflected voltage wave. Here, in the same manner like voltage, current also travels towards the load and some of it is reflected back. So here in the I is the incident current wave, IR is the reflected current wave. Voltage V consists of incident and reflected components. When the load impedance Z is equal to conjugate of source impedance, the terminal current becomes the incident current. It is calculated as as the equations given below. Here, I equal to Vs source voltage divided by conjugate of source impedance plus source impedance. As we know that if a complex number is added with the conjugate of itself, then only the real part is remained. So in the same way, it is equal to Vs divided by 2 times of real part of source impedance. As the definition of the current flowing in the microwave circuit which has a mismatched impedance, this is the equation or to find out the incident current. In the same way, we can find out the incident voltage. As we know, as per Ohm's law, we know V is equal to current times multiplied with resistance or impedance, in this case impedance, as we are dealing with the complex terms of each and every component. So Vi is equal to Zs conjugate multiplied by Vs divided by source impedance conjugate plus uh, source impedance, that equal to source impedance conjugate multiplied with source voltage divided by 2 times of real part of source impedance. As we know, the impedance power, incident power is a real value. So we are going to consider the real part of the incident voltage multiplied with the conjugate of the incident current. So that is equal to square of source voltage divided by 4 times of real part of the source impedance. Scattering matrix. The incident power can be presented in normalized using equation incident voltage. So if you normalize it with the VI equation, then VI equal to VI square multiplied with real value of source impedance divided by mode of conjugate of source impedance squared. So now let us assume A is equal to square root of incident power and B equal to square root of reflected power. Normally, Normalized incident voltage wave to be defined as the square root of incident power. So here A is the incident voltage wave, B is the normalized reflected voltage wave. So these waves are traveling forward towards the load and reflected back from away from the load. These voltages, this A is the forward traveling wave, B is the reflect traveling wave, and those values are given in the slides. If you As we can see in the slide, there is an equivalent circuit model of two-port network. If we consider any kind of two-port network, we have to analyze its equivalent model to study the scattering matrices. So here there is a two-port network which is excited by voltage source and load voltage. Due to these excitations on both the sides, V1 voltage V1 and voltage V2 has been applied on both sides of the network, and it leads to flow of current I1 and I2 towards the network. So the scattering matrix are given as below. B1 and B2 are the reflected waves. A1 and A2 are the incident waves. So S11, S12, S21, S2, S222 are the scattering parameters. As we analyze the Z parameters, in the same way we can analyze the S parameters. Here, basically, in layman terms, S parameters like S11, S12, S21, and S22 are the voltage waves. So, in order to find the power, we just have to square it. As these are the normalized one, we no need to multiply with the impedances. We can directly get the power values. That is just a small tip. So if we see here, S11 and S22 are the reflection coefficients, S21 and S12 are the transmission coefficients. What is the difference between reflection coefficient and transmission coefficient? Reflection coefficients are the values of the waves or the voltage waves that has been reflected back in the same port. For example, if you consider the notation S11, there the both the ones represents the same port 1. If you consider the notation S22, there the notation 22 represents the same port 2. So when you inject power in the port 1, uh, and you it is then S11 is the S parameter that gives the information about the reflected power that has been coming out of the same port. So here, if you consider S21 and S12 are transmission coefficients, if you consider S21, here 1 is the port 1 and 2 is the port 2. In layman terms, port 1 is the input port 2 is the output port. So S21 gives us the data about the voltage wave or voltage power that has been given as input in the port 1 and getting the output from the port 2. In the similar fashion, S12, we can analyze this kind of parameters to understand the performance of the network. Transmission and reflection coefficients are defined as S11 is equal to B1 divided by A1, where A2 equal to 0. Here B1 is the reflected wave from the port 1 and A1 is the incident wave at port 1. S21 is equal to B2 by A2. Uh, B2 is the reflected wave from port 2 and A1 is the incident wave at port 1, where A2 equal to 0. If you consider the certain assumptions like A2 equal to 0 and A1 equal to 0 and substitute these parameters in the scalar form equations of the matrix S matrix, then we can achieve these kind of results: S11, S21, S12, S22. So now we will discuss some properties of S matrix. It is a square matrix of with order n cross n. Here n is equal to number of ports. If the network is lossless, then it follows the unitary property. What is unitary property? If the conjugate of the scattering matrix If the transpose of the conjugate of the scattering matrix is multiplied by itself, then it gives us the identity matrix. If this property satisfies, then the network is assumed to be lossless, reciprocal of a network. If the network is reciprocal, then the transpose of the matrix is equal to itself. Then Sij equal to Sji. Here I means rows and j means columns. If the network is perfectly matched, then the diagonal elements are always equal to 0. We have to remember all these points which helps us to understand the network properly. For proper understanding of the S parameters of a network, let us consider a four-port network. Here, the model or equivalent circuit or just it's a model of a four-port linear network. Here, A1, A2, A3, A4 are normalized incident waves. B1, B2, B3, B4 are normalized reflected waves. Then scattering matrix is equal to B matrix B equal to scattering matrix multiplied by incident matrix. So here there is a general notation of the scattering matrix. If n is the order of the matrix or n equal to number of ports. If we consider a 4-port network, then n equal to 4. If we consider a 2-port network, then n equal to 2. Normalized equations of four-port network. To understand these S parameters, there are few equations that we can analyze so that we can understand the network or S parameters properly. Sij is defined as a ratio between normalized voltage wave reflected at I port and normalized voltage wave incident at J port. Sij equal to normalized voltage wave at I port divided by normalized voltage wave at J port. For example, if you consider port 1 in this 4-port network system, S11 equal to B1 divided by A1, S12 equal to B1 divided by A2, S13 equal to B1 divided by A3, S14 equal to B1 divided by A4. If you want to calculate the total reflection wave at port 1, just we have to rearrange the above equation and we have we can get the total reflected wave b1 equal to s11 a1 multiplied with a1 plus s12 multiplied with a2 plus s13 multiplied with a3 plus s14 multiplied with a4. Similarly, total total incident wave, we can get the similar equation if we just rearrange the above equation. A1 equal to b1 divided by s11 plus b2 divided by s21 plus b3 divided by s31 plus b4 divided by s41.